Thank you.
All right. Thank you all for coming to our talk, Eastern Promises. My name is Laszlo Szapula, also known as LaTsa. And I'm here with my fellow researcher, Laszlo Radnai, also known as Rx7. And we will cover the joint work with our team members at TASZK Security Labs. And we will show you some examples that we experienced during our past several years of research. And I want to shout out for our current and former team members who participated in these researches. So, in the last 5 years, we participated in many bug bounty programs, specifically mobile VRPs. And we had many success stories, in fact, but also we had many failures as well. And we wanted to give you some advices about these things, which you might encounter if you start working in mobile VRP. And we specifically speak about Asian vendors, hence the title of the talk. And hopefully you have something useful you get out of this. So the first chapter will be about our older bugs, which are already published in our advisories or blog posts. And we want to go back into the past to show you some patterns which emerged during the bug bounty programs we participated. And there were multiple patterns. For example, there were target exclusions, there were buffering severity decisions, and there were odd disclosure timelines that were really emerging time to time again. And we just want to show you one or two examples of that. And just to make sure, our goal isn't to bash vendors here, but we want to share lessons which you can use. So the first story is about target selection. Back in the time, we were invited by UOI to join their bug bounty research program. And the first thing we did is we read the rules about their baseband, which basebands they include in their bug bounty program. And we ended up finding multiple bugs. There were RCE bugs in the 2G stack in their Helio chipsets, which are manufactured by MediaTek. And there were also 2G RCE bugs in their Kirin chipsets, which are UOI's in-house chipset. And hands out for our fellow researcher Laurent for finding these bugs and reporting these. And what our responses was, well, for the Helio devices, they said that they are out of the boundary of their bug bounty program. And for the Kirin bugs, although Kirin the chipset is in their bug bounty program, but the bugs we found were in the third-party library, which wasn't included in the newer devices. So yeah, they said no. But nonetheless, we had a happy ending because we contacted them, and in the end, they modified their research program descriptions, so these gaps aren't there anymore. You can see what are the concrete targets that they accept, and they nonetheless gave us rewards for these bugs because they said that the reports were high quality, so thanks, Laurent, for that. And if you want to see technical details for these bugs, I recommend you to watch our Black Hat talk from 2021 called How to Tame Your Unicorn. And if it's not enough for you, we have also a 100-page long white paper about this topic. All right, so what are the lessons here? The first lesson we want to give you is that you should develop an infrastructure with which you can easily check out firmware versions fast without having to reverse engineer them from start to finish. And with which you can easily see if some third-party library was used in a previous firmware version and rate or not. So you don't get into this trap that we got into. And another lesson is that you should play around with these bugs. You should do some trial and error reporting bugs because sometimes the bug bounty descriptions are not exact. So they might differ from what you understand from them. And another point is you shouldn't always go for the newer target, despite of that, because newer targets tend to be harder to reverse engineer, and they may have a different difficult attack surfaces. But other targets may be easier to pawn, but sometimes they are also included in their bug bounty programs. All right, next type of category that we have to talk about is target submission times, or rather which is the good time to submit and which is the wrong time to submit bugs. We don't want to mention specific examples here, but strictly the point, you check out some new attack surface or some new component in a firmware, and you find a good bug, and you report it, and you get a nice reward for it. And then you are hyped. You look for some more bugs in the same component, and you report them, and you might think, okay, I will get many more rewards for that. But sadly, the reality is that novelty is a keyword in these situations, because if you report something that is novel, and you get a reward for it, the vendor won't just sit on this bug. They will try to analyze this component and these type of bugs. They will search for it in their firmwares. And if that might occur that you report more of these kind of bugs, and either they will be duplicated or they will give you much lower reward for them. And this phenomena is sadly real, but this might push bank hackers to hoard their findings, so this is not a very positive thing. And the next topic is disclosure timelines. So you might know that the industry standard timeline is 90 days. But as this example will tell you, this is not exactly true every time. This story is about Samsung full chain vulnerabilities. We found multiple bugs in the GPR stack in Shannon baseband, which were RCE vulnerabilities, and we also found pivot vulnerabilities in their remote FS systems. And we submitted them on the early April of 2023. And after 2 months, we started to asking about their fix status, what is happening with them, and we got no response. We started to asking them again. We asked them for 2 more months. And finally, we received a reply in the following August. And they said that these bugs will be disclosed on 6th of November, which was bad news for us because we were planning a talk, basically a conference, about these bugs. And the disclosure was 1 week after the conference. In comparison, there were we keep checking the security bulletins from Samsung, and we seen that there were 23 baseband bugs with varying severities, and most of them were disclosed after 3 months, and 2 of them within 4 months. So that was off-putting. But the lesson here is you shouldn't assume that 90 days is the hard timeline. In reality, you might wait much longer for disclosure processes. And this can make the researchers very angry. And sometimes we even went into this trap that we start looking at targets because of these experiences, and we also skipped some target ideas altogether. And later, we nevertheless found great publications by other good researchers. So the lesson here is don't let the anger drive you. You need to look at the bug bounty programs time to time again because they change over time. All right, these were the past experiences. Now we will talk about bugs that were not published until recently. In chapter 2, I show you an example how the misinterpretation of the vulnerability research program description can go wrong. And this vulnerability was found in 2021, but it was disclosed last May, this May, sorry. And this is about Huawei hypervisor. If you are interested about this specific target and these bugs, you can check out my talk at Off-by-One conference, Don't Believe the Hypervisor. But quickly about here, why we should attack a hypervisor. Well, in modern mobile phones, kernel mitigations, exploit mitigations, and such are implemented using the hypervisor itself, which is an architecture-based protection. It has multiple features that you can use for exploit mitigations. And what research setup we had is we assumed that we have a kernel memory read-write primitive with ASLR leak, and our goal was to go open a shell, which is not straightforward, for example, at Huawei. But why Huawei? Well, in their vulnerability research program, they said that exploit mitigation bypasses were of high severity, and they were rewarded with in the high category. And HKIP, which stands for Unified Kernel Integrity Protection, is defined as an exploit mitigation. It's an exploit mitigation, even in the white paper. And we were, all right, let's look for bugs in there because that might give us some nice rewards. And what they did was they used the stage 2 translation of the ARM64 hypervisor layer, which basically adds an extra protection to the memory, kernel memory. Basically, you cannot overwrite kernel page tables to modify read-only pages to read-write pages. And they use this to protect critical structures like credentials, SA Linux context, and such things. But of course, for some mitigations, you have to be able to turn this protection on and off because, for example, if you want to protect credentials, these credentials are, allocated when a new process is created. So you have to be able to do that. And I did this by adding a kernel API to the hypervisor. And the issue was there that there was no verification for these calls. Basically, you were in any kernel context in the kernel space, and you could use HVC, which is the instruction to call the hypervisor. And with that, you could call the hypervisor API calls to remove these protections or even override the data on these memory regions. And these logic bugs were reported. We found them in late 2021, and in the following spring, we also started working on our emulator and the fuzzer. So let's see a demo here. You can see that you cannot even list the content of the root file system because SA Linux stops you from that, and you can't even open files because of your permissions. But we run the exploit, and when we trigger the HVC calls using a power button press, we have overwritten the credentials and the SA Linux structures, and we are now in a fully privileged shell, and we can open files we want to. So, yeah. All right, what was the response here? In May 2022, Huawei responded, and what they said that these bugs were out of their scope, and what reasoning was is these are not exploit mitigations, but things that make attack more difficult, which was off-putting. But we also reported kernel vulnerabilities, some of which were critical severity, and they at least give us good rewards for that, so that was nice. And what the lessons here is that you should really read the whole VRP description slowly, and you should really understand, you should be careful about what you submit, what you're looking for. And you should note that vendors like to think inside the box because they said that these logic bugs weren't bugs, but they said also that if there were code executions in the hypervisor, they would accept it, so yeah. All right, in the last two chapters, we will talk about severity rating the differences. In this chapter, I will talk about a bug I found in 2023, and I'm disclosing it now for the first time. And this also had happy ending at the end, kind of. And in the final chapter, we also have this kind of issue, but let's not get ahead of just yet. Let's talk about trusted execution environments. So why we want to attack TEs? Well, because they also are a hardware-based security feature which separates memory from non-security secure. And basically, you cannot access secure memory from non-secure context. And our research environment was the assumption that we have a kernel LPE. And our goal was to get code execution in the TE. And if you want to know more about trust zones and security research inside them, there is a non-complete list of many good researchers. I recommend to read them if you're interested in this topic. But a quick 101. In ARM64, the architecture core can be in one of 7 states, and there are 2 axes you can separate these states from each other. One is the exception level. Basically, the higher the exception level is, the more privilege the core has at runtime. And on the EL0, you have the user space applications, and the EL1, you have the kernel itself, and the EL2, you have the hypervisor. And the other axis is the secure, non-secure separation. Basically, if you're in a secure state, you can access memory that is marked as secure memory, but you cannot if you are in non-secure memory. This is enforced by the hardware itself. So the only way you can get into secure world is through the trusted firmware, which lies in EL3. Our target was Unisoc. It was formerly known as Petrum, and they manufacture mostly chipsets for low-end devices, and they're selling them mostly in Asian countries. And it's not easy to find these in Europe, but we were lucky with the Samsung Galaxy Tab A8. Checking out their firmware, we found out that Unisoc's TASZK implementation is not fully black box, luckily, because they rely on Trusty, which is Google's TrustZone implementation, which is fully open source. And they also comply to the global platform API in their trustlets, which is also which makes our reverse engineering effort easier a bit. All right, if you have a Samsung device, the firmware acquisition is quite straightforward. You can go on the internet, you have multiple sites, you can download any firmware for every device for every date. And if you open this package, you find multiple tar archives, one of which starts with BL, which stands for bootloader, and inside this you can find the TrustZone and the trust firmware itself. And the TOS signed bin is the Trusted OS binary. And as its name suggests, it's a signed binary, which also includes the Trusted OS and the trustlets. And this is how it looks like. In the first 512 bytes, you have the DHT header, which is a descriptor and such. After that, you find the Trusted OS, which is a 64-bit ELF binary. After that, you have the trustlets, which are 32-byte ELF binaries. And in the end, you have the signature for the whole package. I started reversing these trustlets, and by looking at some strings, I quickly found out what these trustlets were, what functionalities of the trust zone they implement. So, for example, you have keymaster, which stores keys in the secure world. You have gatekeeper, Gerner boot CP, which is for secure boot. And what I did is I was starting to reverse the common parts, and also I was looking for parts that were vendor-specific, which tend to be quite error-prone. And that's when I came to trust the Crypto trustlet. This basically implements the DRM protections. You might know DRM from Netflix, for example. This trustlet can run in two modes. One is Widevine, which is Google's own solution, which is a VM-based mesh, basically. And you have also Unisoc Crypto, which is, as its name suggests, vendor-specific. And by default, it is used in this chipset. By looking at this trustlet, we find many API handlers, many used for different crypto procedures. And by looking through many of them, I got to this function decrypt CENC. The CENC is used to decrypt DRM-protected binaries. And if you like pwning in CTFs and such, I think you almost immediately find the bug here. You have 3 little buffers on the stack allocated, and if you look a little bit further, you can see that there are multiple memcopies, and you have the vulnerability right here. Basically, you can provide a size that is used for memcopying to the stack. Nice throwback vulnerability. All right, we have a bug, and how can we trigger it? We can open the trusty IPC dev device driver on the kernel from the Android side. This driver has specific Linux context required, and it requires also for specific system users and groups, but we use the rooted device, so that didn't stop us in the research. And what you can do with this file, you can open it, and you can use IOC to connect to trustlets, basically, to IPC. And this is the way we triggered the bug. We called open on this file. We used the IOC tool to connect to the Crypto trustlet. we use the pwning function to initialize the DRM functions. And now we could call the decrypt C and C function with a fairly large size using to copy, and there we have the overflow. And if you look at the checksec output for this L5, you can see that this is also a little bit rollback for the all times or baby CTFs. Basically no protections, but you must take it with a little bit of grain of salt because we didn't reverse the loader in the trusted OS. But I confirmed that there is really no stack canaries and no ASLR in this binary, so exploiting it was not that difficult. I just put together a simple drop chain, which put a string on the BSS, and I called a log function with the string because logs from the trusty, you can see them in the message, and I returned to the message handler, so the trusted didn't crash. And here is a really quick demo. On the bottom, you can see the dmessage output. And on the top, I will run the exploit file, and that's it. You have code execution in trusted environment. All right. After the submission, we had good news and bad news. Good news is that they disclosed these CVEs fairly quick. We submitted them in May 2023, and after the bugs were published in the bulletin, we asked about their vulnerability research program, but sadly they said that they stopped the research program just as we sent in the bugs. So yeah, no VRP for us there. So programs really changed, so lesson is here, you should look out for these things. But as I said, the timeline was for the fix is quite fast, so that was a positive. And for the severity, we also were surprised because at first they said that these bugs were medium severity, but later they modified it to high. So thank you, UNICEF, for that. So what are the lessons here? Well, according to the rating, you shouldn't accept that every vendor's assessment of bug severity is identical. CVSS is not good for mobile bugs because in multiple mobile firmwares, for example, as you see in trusted execution environment, you don't even stack canaries. So bugs which are not that usable, for example, in the Linux kernel, they are quite usable in the mobile phones. And as you can see, we picked a model totally randomly, this Samsung Galaxy, because that was the only thing we could access in Europe. And we were still successful with that. These bugs were still an issue in other products using this chipset. All right, now I give the microphone to my fellow researcher, Laszlo, to talk about MediaTek emulation.
Hi. In the final part of the talk, I will be talking about vulnerability research that spans from 2023 to 2025. This is also a story about severity ratings, as Laszlo have mentioned, but not with a very happy ending, unfortunately. So, baseband is basically a set of processors that handle connectivity stacks, exposes some remote attack surfaces which are often zero-click, so doesn't need user interaction, and in some cases these are also end-to-end. While researching, you have to be careful, you have to consider what access do you have to the mobile device. Does the attacker reach this part of the attack surface? Our goal was to compromise the baseband runtime, find the highest impact bugs in the sense that no privileged access is preferred. And also I want to know that compromise also means DOS. If you can crash a device's baseband perpetually, this might be a high impact bug for vendors. So I targeted VOLT and do check out these blog posts and talks. For emulated baseband fuzzing, also check out base-safe firmware, base bridge, and securing the airwaves. So what is VoLTE? In classic cellular networks, the code setup is done over the control plane. However, in modern networks, they have adopted voice over IP for calls, and this means that all call setup and stuff like that is set up over IP, and the actual data is also over IP. This means SIP, which is responsible for the state management and protocol, SDP for describing and agreeing on codecs, and RTP contains the actual data. Now, this is not over the internet attack surface, this is over the IMS, which stands for IP Multimedia Subsystem. It's a completely separated data traffic, and VoLTE and the other technologies are basically VoIP over IMS. As an attack surface, it's really interesting. You have text-based protocols, binary protocols, and specifically audio-video codecs with different reachability properties. And the parsers, encoding, and stuff like that is typically implemented in the baseband. As such is the case for MediaTek. So yeah, nice. And I also want to note that our target was assuming a compromised IMS core network, or finding bugs that are actually end-to-end exploitable from another mobile device. I want to note that this end-to-end is possible. SIP is end-to-end on paper, but it also needs to partially re-encode some headers for routing. Also, it might filter SIP packets if they are malformed or just can't route it to the proper place. And this doesn't mean that this stops any malicious SIP packets. For example, in the UK, there was a case where a mobile network operator leaked sensitive data, exposed internal headers, and also forgot to sanitize, basically, forgot to filter sensitive headers. But there are other stuff. When discussing attack surface of a feature, always check how it plays with roaming. SIP is HTTP-looking communication protocol. It can go over TCP or UDP. And what I will be talking about is after you register to the network, to a SIP server, basically, you can initiate and receive invites, which are the first part of the call setup. This invite looks like HTTP if you squint hard enough, but the headers are different and stuff are different. Just like HTTP, you can actually add and will add content and the body. This is SDP. This content is SDP. It's almost a key-value pair, but the order matters, so I wouldn't call it that. This describes, for example, what kind of audio modules are supported. Now we have seen what is SIP and SDP. This is our main target. How to target this? Because of the multitude of headers, we have decided after a short reverse engineering run to set up emulated fuzzing for this target. Now there are many components that need to work together. So we have decided to use libafl, which can you can use different parts of the fuzzer in different. You can plug in parts of this fuzzer from different use cases. That's why we have emulation and grammar fuzzing and some support for catching overrides, subtle overrides, like one-off, and which would hit padding or something like that. So we can use QEMU, emulate the VoLTE stack by calling into the entry point, which parses the IP packet, like TCP packet, and we have used grammar fuzzing for detection. There are many solutions, but we have decided to hijack the allocator, so allocator requests, so that we can introduce more checks. MediaTek's basement is quite reverse engineer friendly. We have a ton of debug symbols, so building a harness wasn't that hard. The main issue was implementing nanomips architecture support for different tools we have used. And also there was a challenge for emulation. We have lots of state machines at hand. We have complex hardware-related codes. So for the first part, you have to be registered to the SIP network in order to receive packets on the already set up TCP session. So how do you do that? We have leveraged RAM dump of the baseband runtime's memory, which is correct in a point of time where this was correctly initialized, and we got the correctly initialized state machine values from this baseband, from this firmware image, basically, and our approach was really similar to Bracebridge, so it's, yeah. Yeah. Also, I want to note that we have used grammar fuzzing. Do read up on that. I won't be talking much detail about this. We have decided that keywords are not enough, smart corpus generation is not enough, large set of valid inputs are not enough to fuzz this, fuzz the more complex code paths. So we have decided to create some context-free grammar with Nautilus and basically use that. And we have also tried mixing bit flipping fuzzer with context-free grammar fuzzer in order to have more results. This kind of worked, and we had crashes. We had many crashes. We had so many crashes that we found that we actually have to pack. Yeah, this is the fuzzer's TUI from 2 years ago. We had so many bugs that we found that this slows down the fuzzer, so we actually had to patch the bugs for ourselves in order to continue reaching deeper execution paths. Next, I will describe one of the bugs we found. This is basically a buffer overflow when decoding the mode set parameter. You can see that this is a set of integers separated by commas. MediaTek's implementation supports 16 of these slots in the output structure. Hence, they restricted the input length to 32 characters. So, if you forgot to introduce bounce checking, introduce error handling, you have a problem. This problem is that you fill the slots with empty integers, which get parsed as zeros, and you can actually, so this actually fills 1, 2, 3, 4, 5, 6 after the end of the buffer. The other findings are listed here. Once again, I want to credit all the team members who worked on this project. So, yeah. We can see that many of this was like too many of this something leads to buffer overflow. One specific case is replacing a single quotation mark with 10 characters, which fills the buffer of the same length destination buffer. And I want to note the last one, because it's a stack recursion, stack unbounded recursion. This is basically, you can create comments with parentheses, but you have to actually know how deep you are in the comments. So they have used a recursive approach to find this, and I will showcase our tooling for this. So there are many open parentheses characters, as we can see. We run our target with our emulated target here. It crashes, but we can also debug this, which means that we can put a GDB on this, and we have breakpoints, we have single-step debugging, and also when it crashes, and we can actually inspect the stack state, which shows that there are several levels of calls deep in the call stack. This is nothing new. This is just convenient tooling. And here comes my favorite 2 slides. So we got critical to the heap overflow issues first, then they were lower to medium, and the vendor responded that heap overflows can be exploited due to a mitigation that is similar to sanitizers. Quick back and forth, and yeah, please note the legal disclaimer. Feel free to understand these quotes as the figment of our boss Daniel's imagination. On our legal counsels of advice, we are not claiming that they are valid quotes, but we included this in our talk strictly for entertainment purposes only. So, while you read this and weep, once again, I want to point out that we don't have MediaTek's express permission to quote their responses verbatim. Therefore, for legal purposes, this is not an actual quote from them. So, we have an ongoing disclosure with this because after this response, we have decided that we lack the resources for going on with this project. So we had backlog of like 20,000 crashes. Finally, we got around to actually do it. We have created root cause analysis. We duplicated the bugs written reports, and we have verified the liveness in around the end of 2024. So we have 11 reports. These might not be actually full on 0 days. Since we haven't had the time to redo liveness checking for the time lag between when we last had free time to do it and when we finally complete the deep duplication and report writing work. So these are just reports of 3 heap overflows, 1 stack overflow, 1 mem leak, and 6 DOS type bugs. We actually didn't use MediaTek's bug bounty program this time. Reports, however, still included the root cause analysis, and this did to replicate POC instructions. We directly contacted the MediaTek's security team for this. And we intend to publish this in 90 days as per our disclosure policy. And on a closing note, I want to say that maybe we do need to relearn some lessons from the past. This is Dennis Fisher, by the way. Yeah. And thank you. Any questions?
Sorry? Oh, really? Okay. Okay.
Hello. Yes, so I have a question. Yes, so you've talked about downloading a firmware on the internet. I'm really surprised that it's not encrypted. in the case of you, like you don't find the firmware on the internet, do you do a chip-on or chip-off firmware extraction on the hardware, or you just call it a day and change over target?
Whatever works for you, basically.
Ah, okay.
One question here.
Yes, ici. Il y a une question.
On va passer à la conférence suivante.
Il voit pas.
Allô, allô.
Sorry. You have a question? Yeah.
Je suis désolé, on est obligé d'interrompre pour passer à la conférence suivante. Voilà. Merci de remercier Laszlo Radnai et Laszlo Szapula.